Let's do another example from 7.4. So remember we discussed in the first example that sometimes it's nice to do a substitution where instead of substituting an expression and calling it U or W or your favorite letter, that you actually want to use a trig substitution. And the way to do that is you visualize a triangle and then you call your x or your x over 5 or your x over whatever some form of a trig function, and that actually makes the integrand easier to work with. We saw previously an example using tangent of theta to replace x over 4 in that example. Now we're going to look at an example where sine makes more sense. Notice now we have the situation where the expression in the integral looks like the form 25 minus x squared. So that's in the form a squared minus x squared, if you recall the forms where trig substitution works out from the previous video. And so in this case, when it's minus, we're going to notice that sine, in fact, is the better choice. The reason is, if I look at the triangle, I have some angle theta, and if I decide that I'm going to let the sine of that angle theta be equivalent to x over 5, when I look at my right triangle, that makes this adjacent side right here the square root of 25 minus x squared, which of course is the expression, whoops, didn't want to cross that out, that I have here in my integrand. So that way, using some right triangle trig, I can substitute out a complicated algebraic expression for an easier trig expression. Once you establish that substitution, you work it through pretty similarly to how you do a U substitution, and sometimes you just need to bring in a few trig identities. So let's go ahead and try this one. So what we had here was the integral of x squared over the square root of 25 minus x squared dx, and we decided the best substitution here would be to let the sine of theta equal x over 5, which means x is going to be 5 times the sine of theta. So following our rules for substitution, I now need everything in terms of theta. So I need an expression for dx. So taking the derivative, I'm going to get that dx is going to be 5 cosine of theta d theta. Now I'm going to substitute with the goal being what I get to integrate is going to be easier than what I started with. Notice here I can substitute dx with the 5 cosine theta d theta. And then wherever I had an x, that would be replaced by 5 sine theta. So substituting that in, 5 sine theta squared is going to be 25 sine squared theta over the square root of 25 minus 25 sine squared theta. And then my dx becomes 5 cosine theta d theta. A quick comment, and we'll discuss it more in class, or you might want to pause and think about things for a minute. Because remember, if we're going to go back up for a second, we're calling x and 5 actually represent sides in our right triangle. So in order for any of this to make sense, we're assuming that theta, when we define our theta, is an angle between pi halves and negative pi halves, so that I can solve for the arc sine. I'm also assuming that x has to be a number between 5 and negative 5, because otherwise my radical in my integrand is not even defined. So if x is between 5 and negative 5, that is going to force my theta here to have to be an angle between negative 90 and 90, or pi halves and negative pi halves. Furthermore, since I can notice here that in this particular interval, if x has to be between 5 and negative 5, my cosine of theta, which is going to be adjacent over hypotenuse, right? So the adjacent side over the hypotenuse would be cosine, is always going to be a positive number, because 5 is positive, the radical is always positive, so we can assume that the square root of cosine squared is just positive cosine. So those are things that probably won't actually, you would assume automatically as you're doing the calculations, but they're justified in our setup. So now we just want to simplify. So from here, what I would first do is factor out a 25 and reduce things that I can. So, whoops, let's go back to our regular pen here. So I had the integral of 25 sine squared theta in my numerator Here I had the square root. I'm going to factor out a 25. As you get a little bit better at this, you might be able to do this in less steps. As long as I can see what you're doing, that's fine. And then we had the times 5 cosine theta d theta. Notice here that my 25 is in the square root, right? So I'm remembering, of course, that the square root of 25 is, of course, 5. So when I reduce the square root of 25 with the 25 in the numerator, I can pull out a 5, and then I have times this 5 over here, right? By over here, I mean over here. So if I look at all my constants in yellow, my square root of 5 divided with my 25, this is going to give me 5, right? Sorry, square root of 25, which is 5, reduced with my 25 is 5, times this 5. I'm going to pull those out of the radicand. And then I'm still left with, of course, sine squared in the numerator. Now I can replace 1 minus sine squared with cosine squared. Oops, I forgot my theta. And here I still have cosine of theta d theta. And of course, like we talked about, it's safe to assume that the square root of cosine squared is positive cosine. So remember, we were defining theta was that angle in that right triangle, and I know that cosine of theta has to be a positive number, so that therefore the square root of cosine squared is just cosine. So what I've highlighted in green will reduce to 1, and I, of course, oops, there's my d theta. I'm going to still have the d theta. So here this is going to become 25 integral of sine squared theta d theta. Right? So doing this trig substitution, although I need a few trig identities on the way, actually allows my integrand to become simpler. Now I can integrate in terms of theta. When you integrate in terms of theta, you have two options here. You can look on the table and figure out what the formula is for the integral of sine squared, or you can do by parts. In either case, I'll say by table or by parts, and I'll let you guys verify that on your own. When you do that integral, you should end up with negative 25 over 2 sine theta cosine theta plus 25 over 2 theta plus c. Now as our final step, we need to put all of these things back in terms of x. That's where having a picture of the triangle is actually a good idea. Remember, if this was my angle theta, we have the opposite side is x and the hypotenuse is 5, because that was our substitution. We said, let's say that the sine of theta is x over 5. That was the substitution we wanted. So by the Pythagorean theorem, this side, of course, would be radical 25 minus x squared. So I realize, of course, my original substitution was that the sine of theta should be x over 5. That's what I set up. Some simple right triangle trig lets me realize that the cosine of theta, which is adjacent over hypotenuse, is the square root of 25 minus x squared all over 5. And then theta itself, of course, right, if the sine of theta is x over 5, theta would be the arc sine or inverse sine of x over 5, right? So now, using all of this stuff in green, I can substitute everything that's in theta in terms of x for my final answer. So when we do that final substitution, we get that our final answer is negative 25 over 2. X over 5 replaces the sine of theta. Radical 25 minus x squared all over 5 replaces cosine of theta. Plus 25 over 2. And arc sine of x over 5 replaces the theta, and then of course plus c because it was an indefinite integral. To sum up a little bit of our rules, we said whenever you have an expression in your integrand that looks like a squared minus x squared radical, you want to use a substitution where you're going to let the sine of theta equal x over a, and that's a substitution that will usually work out nicely. And if you have either a squared plus x squared or radical a squared plus, that's supposed to be squared, plus x squared, you would want to let the tangent of theta equal x over a. And then if you follow the substitution process, just like with a u substitution, you should end up with something that you can integrate Again, either with one of the other methods we've learned or using the table, you'll get something that you can integrate more easily. Don't forget to substitute everything back to be in terms of x, and sometimes, like we had in this problem here, you need to refer back to the original triangle in order to really get a nice expression in the end. So that's basically the integration with trig substitutions. These are the cases, right? These three cases, if you have one of these forms in your integrand, are the times when using a trig substitution would be helpful. If you're doing more research, you'll notice that, of course, we have other trig functions between sine and tangent. There's other trig substitutions that you can do. Most of the problems that we're going to look at for practice are going to be using either a sine theta substitution or a tangent of theta substitution. One little trick that I usually use is that plus looks like a t, and that reminds me that when it's an expression with the plus, that's when I use the tangent, and if it's the minus, then I use the sine.